Everyone, and welcome back to this morning. This is kind of the meat and potatoes, so to speak, of of part two, and it's because this is where we're gonna put all the things that we've learned together, with unit conversions and rules of fractions, and then some of the stuff with molar mass ratios and stuff that we discussed last week. We're gonna put it all together into one thing. Because I do believe that everyone except for one person did say that they were here last week. So um, there'll be, though molar mass isn't something that's overly concerning. But yeah, I think with that, we can go ahead and turn over to the very first poll question with Matt so that we could get started, because with stoichiometry, there's a lot. There's no way I will get through the entire question packet in the back end with you all. So.
All right, so you should see this first question up on your screen. This is a routine question that we ask that helps us with our metrics of how many people attended this course or this course session. So if you can take a moment to answer that, and I'll let this run a little bit until we get up good over 90%. And we are, but looks like I've got a few people that have not answered. If you do not need continuing education credits, certainly you do not need to worry about the poll questions. But we are at 97%. I'll let this run another 15 seconds, and then we'll turn it back over to Scott and get this session going. Okay. Let's see, end the poll here and turn it back to you, Scott.
All right, with that being said, let's go ahead and get the PowerPoint started. All right, so we are going to be talking about stoichiometry. All right, so stoichiometry or stoichiometry, or it gets pronounced, I call it stoichiometry. It gets called a bunch, it's pronounced differently by lots of people, but so are lots of things. So this is quote unquote the unit conversions of chemistry, okay? And it is, to be honest with you, the fundamental basis of all basic chemistry class. So if you have high schoolers, what you learn today, you will definitely be able to help them 100%. If it makes sense, if you make sense to this, understand it, you will be able to use this to assist your high schoolers in chemistry. I promise that what I'm going to show you is exactly what they are supposed to and hopefully learn in high school for sure. So what the general thing is we're going to be doing and trying to understand the general understanding of what it is. What is a mole? And by that, I do not mean the furry creature in your front yard. Molar ratios, molar mass, mole ratios, and then kind of putting it all together based around the balanced chemical equation, all right? All right, I'll let Matt deal with that one. So, of course, now I do that and it messes it up. All right, general understanding. So stoichiometry is the process used to determine the amount of reactants and the amount of product that will be produced through a chemical reaction. So theoretically, we are going to be assuming that every reaction runs 100% and it goes 100% from products or from reactants to products, okay? That is not how it works in the real world, but we are going to use that, okay? And stoichiometry works on the law of conservation of matter. And if you remember what that is, it's simply that things cannot be created, nor can they be destroyed. And if you remember, the guy who came up with that was the father, and he's a French guy by the name of Antonio Lavoisier. We talked about him a little bit last week. So the conservation of matter is what stoichiometry, how it works is that allows us to convert from whatever reactants are to the amount of product we are expecting to see, okay? So with knowing that, you can kind of figure out how many of certain amount of chemicals you need to yield what you're looking for. Then again, like I told you, in the real world, that isn't exactly how it works. In the real world, you'll say, I need this much of this and this much of that, and I should get, we'll just say I'm looking for 10 pounds of water, whatever. So if I put in this many pounds of hydrogen, this many pounds of oxygen, I should get this many pounds of water. And then you'd weigh it and be like, what? A lot of reactions only go to 70 or 80% yield, maybe up to 90, depends on the reaction. But there are some reactions for certain things in industrial processes that will literally only go like 50% without any intervention, okay? We won't talk so much about the intervention that scientists and people use on that stuff, but you can force chemical reactions more towards products and reactants. It's just sometimes it takes special things to do so, all right? So the mole. So over the centuries of chemists, we were trying to figure out a universal concept that would understand and get us something of significant size, okay? So trying to quantify a group of atoms is really hard. The size of atoms is different. Seeing an atom is hard. And only a few thousand atoms is so minute in weight or so minute in size that it doesn't really matter. In the room you're sitting in, there are billions and trillions and quadrillions of atoms, and everything you're at the desk you're looking at, in your body. There's more atoms than you can even guess as far as it goes. Okay. So trying to quantify them into a useful amount was kind of hard. So there was a guy by the name of Avogadro, who I think was a physicist. I think he's Italian, but I don't remember exactly. But either way, a guy named Avogadro came up with what was called the Avogadro's number. And Avogadro's number then became a universal constant that was accepted by chemists all over the world. So it's kind of like the number pi, right? 3.14. So Avogadro's number became a universally accepted number of atoms that would then lend itself to a mass unit, okay? And it 1 mole. So the mole is not the mole in your front yard like I was talking about. We're referencing 1 mole represents a number of particles, okay? And I want to just show the significance of this because 1 mole equals 6.02 times 10 to the 23rd. So first off, a lot of people don't necessarily grasp what that means. Okay, so first off, a mole is just like that of like 1 foot equals 12 inches, right? Or a dozen. A dozen's a better way of thinking about it, right? If I tell you 1 dozen, you go get 1 dozen of donuts, we all know that we're going to get 12 donuts, correct? Well, mole is in that similar fashion. 1 mole, how 1 dozen represents 12, 1 mole represents 6.02. Okay, then I got to go 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23. Okay. So I have 0, 0, 0, 0. Okay. So there's a reason I'm doing this. That's a lot of zeros, isn't it? So just like 1 dozen represents 12, like the number 12 over here on this side. If I wrote 1 dozen, it would equal 12 donuts. 1 mole equals 6.02. And yes, it was times 10 to the 23rd. Well, what that means is you would have to actually see the number. This is the actual number. You would have to add this many zeros behind it, 23. So I moved the decimal places 23 times to show you how big. So there's a comma there, here. And if you think about it, right, 100,000, million, billion, trillion, and then quadrillion, and I don't remember what comes after quadrillion. But this just shows you how big this number is. So first off, this number is representative of anything. 1 mole could equal 6.02 times the 23rd. You could say cars. There's not that many cars on Earth. If there was, there'd be no room to live. All right, and it'd be a junk pile, probably 100-foot thick, covering the entire Earth's surface or something stupid. But the 6.02 times 10 to the 23rd can be used in reference to anything. You could be measuring cars, you could be measuring inches, you could be measuring, milliseconds for all I care. It doesn't matter, you know, because you could get that probably in a lifetime, maybe. But my point is 1 mole equals 6.02 times 10 to the 23rd. This is what the number really looks like, because in order for the atoms to have any mass, you have to have that many of them. Does that make sense? If you don't have that many atoms, the mass of the atom group that you'd be looking at would be so insignificant that we probably couldn't measure it, okay? So what do I mean by that? All right, let's go back to the PowerPoint and kind of put some reference to something like this, all right? So 1.02, 1 mole equals 6.02 times 10 to the 23rd particles, okay? That number can be applied to atoms, molecules, or ions. All right, and keep in mind that a mole of ions or atoms or even molecules are not going to weigh the same, right? That's just like saying every person on this phone call or on this webinar, we all weigh the same. We all know that that's not true, right? We all have a different mass associated with us. We all have a different weight. Mole is the same way. Moles all weigh different. A mole of water does not weigh the same as a mole of hydrogen. Does that make sense? Okay. Well, how much does a mole actually weigh of something? So we've sort of talked about this, all right? So we did molar mass last week, or we did molecular mass, but what we were truly doing was molar mass. So if you recall with water, I can go back to the camera here to show you. If you recall, I was like, all right, how much does water weigh? Water was H2O. We had H has 2 atoms. Oxygen is 1 atom. Times by 1.01, times this by 16. And we got 2.02 grams. And we got 16 grams. And then if you remember, water weighed 18.02 grams. The thing is that 18.02 grams actually equals 1 mole H2O. So that big number, this 6.02 times 10 to the 23rd, it takes this many H2Os to equal that many grams. 18.02 grams, just in case if you're wondering, a lot of people maybe know the conversion, some don't. Some people like to think of this as pounds, right? Or no pounds is a better reference. This is equal to 0.04 pounds, just so you're aware, okay? So we have, you see that big number right there? It takes this many water molecules, or molecules, to equal 18 grams, which is only 0.04 pounds. So do you see why that number has to be so big? That number has to be so big so that we even have something that's measurable and quantifiable. All right. Because if the number was any smaller, it would be almost non-existent. The weight would be almost non-existent here where it wouldn't matter. Does that make sense? All right. Some of your bigger molecules that we looked at, like aluminum sulfate and or that kind of thing, or alum in quotes, is 1 mole of it's barely over a pound. Barely over. It's like 1 1/4 pound. All right. By its molecular or by its molar mass. So when we were doing this last week, we were actually solving for what the true name is molar mass. We just didn't talk about that, okay? So 18.02 grams per mole, or equals 1 mole of water, okay? So here's another one. You remember doing these calculations now? Yeah, just as a refresher, you know what, I'll give you, first off, is there a periodic table in this thing? Let me look. I don't think there is. There probably should have been. Nope, there is not. Okay. So here in the very first one, you know, I I hate PowerPoints for these things. All right. So with hydrogen phosphate, with phosphoric acid, you have hydrogen, you have 3 grams of it. It's 1.01 grams per mole. So the atomic masses that we seen on the periodic table last week, like hydrogen weighed 1.01, nitrogen is 14.01, carbon's 12.01, oxygen is 16, phosphorus is 30.97. Okay. So that atomic mass that we saw underneath the elements on the periodic table is where these weights are coming from, just like we were doing. This is not, I'm not pulling it out. Oops, not pulling it out of a hat. Okay. The 1.01 was what's on the periodic table. 30.97 is what's on the periodic table. Okay. So we're doing the same thing as we did last week. 3 atoms times 1.01 equals 3.03 grams. All right. 1 atom of phosphorus weighs 30.97 grams. 30.97. And then oxygen had 4 atoms and it weighs 16 grams. So we add them all together and we get 98 grams per mole. So the molecular weight was 98 grams, but it weighs 98 grams equals 1 mole of phosphoric acid. Okay. So it's really important that we would write the label of H3PO4 on the back of that mole, kind of like I did with the water earlier. Okay. So what does this mean? Remember, we can write conversion factors as fractions, right? So how that's going to work is with water here. I wrote it as 1 mole of H2O. This pen's a piece of junk. I got another one in here. I do not. I might have to go get one of those in a minute. 1 mole of water equals 18.02 grams of H2O. We need to start making sure that we label these, okay? And if you remember, 1 mole equals 6.02 times 10 to the 23rd. Does everyone agree with that? So I can first off write this. Let's think of it this way. I can work 1 mole H2O over 18.02 grams H2O, or 18.02 grams of H2O this way over 1 mole of H2O. Does everyone follow me so far? All I did was I found the weight of it, and with finding the weight, I came up with a conversion factor. And see, this is where I told you that chemistry, conversion factors are different, but the unit conversion process is the same, okay? The conversion factors for chemistry come from what you solve here and from the periodic table, or from a balanced equation, okay? Do you agree that 1 mole equals this number? 6.02 times 10 to the 23rd. In this case, it would be molecule, well, you don't got to write it, but it'd be H2O. We got to have that many H2Os to equal this amount of weight. So the other conversion factor that can be written here is it can be 18.02 grams of H2O over the 6.02 times 10 to the 23rd H2O, or the other way around, because we substituted this for the mole. And yeah, sometimes if you have a, your teacher really wants to get you, they will ask you how many atom or how many molecules of water would be made in this reaction. And this would be because this tells you how many waters it takes to make that. All right. So it is a possibility to do that. So with finding the molecular mass of something, you found the molar mass of it. That molar mass, as you can see, now makes 2 different conversion factors because of what 1 mole equals. All right. So in this example, how many water molecules are in 6.5 grams of water? Okay. So yes, it's written out there for you, but I am going to go to my paper and I am going to do it for you on the back of these things. Okay. Because I want to walk it through with you all so you can write it down. and get an understanding of what we're doing, okay? So to my calculator, not calculator, to my piece of paper. So it's saying I have, I'm just making this bigger for everyone so they can see better. All right, I'm starting with 6.5 grams of H2O. And that is over 1. Okay, in chemistry, almost the front part here never has 2 units. It's usually just the 1. So 6.5 grams of water. Well, it wants to know how many particles there are in that. And I know that 1 mole of water weighs 18.02 grams of H2O. Correct. And I know that 1 mole of H2O equals 6.02 times 10 to the 23rd of H2O. Okay, so I'm going to do this just like I did with unit conversions. If grams of H2O is up here, where does grams of H2O got to be to cancel? Well, here's grams of H2O right here. It comes from this is from the molar mass that you would find using a, can't even read that. That comes from what you would find by adding up on a periodic table, okay? So 18.02 grams of H2O go here. 1 mole goes there. Well, grams of H2O cancel just like that. See? Now I need to convert the mole to particles. Times 10 to the 23rd. So mole and mole cancel. Now, the big thing here is how do I use my calculator? Because see, times 10 to the 23rd is a weird number, okay? Let me show you how that works. So it's going to be 6.5 times, as you can see there. And then you're going to look for a little, either your thing will have a button that says EE, or it'll have like a 10 times button like this. See where it says 10x here? So you would type 6.02, and then on this calculator, hit second, and that, oh, why did it? I really got to do that on this one. Yeah, I prefer the other calculator. I hate this one. The other calculator, the one that I typically recommend, it has an EE button, and EE means the same thing. So when we do this, it's going to give you this number, 3.913 times 10 to the 24th. Well, now you got to times everything across here and then divide by the bottom number, which is 18.02. So then you just hit divide because it'll move the answer down, and then it's by 18.02. It's going to give me, you only got to go to the second decimal here, 2.17 times 10 to the 23rd atoms of H2O. Okay. So that's still a really big number, 2.17 with 23 zeros behind it, essentially. All right. Okay. So that's how you do the number of molecules. You can use, as you see here, just like I wrote out, it's 1 mole of water. You got 6.5 grams up top, 18.02 grams on the bottom of it for 1 mole of H2O. Then you're going to put 1 mole of H2O on the bottom here, equals 6.02 times 23rd molecules there. And they, as you can see, cancels because top and bottom. Same with that. And then just like that, we get to 2.17 times 10 to the 23rd, okay? Oh, now let's consider the reaction to form water. If you remember this equation yesterday, this is the balanced equation. And now one thing we have to keep in mind is with a balanced equation, sometimes we need to use coefficients in front of them to balance the equation, correct? Well, that number, that coefficient, tells you how many moles of stuff have to react together in order to form how many number of moles on the other side, okay? What? So yeah, scratch your head and think about that for a second. So the numbers that we put to balance the equation, like the 2 here and the 1. So now that there's nothing here, you have to really remember that that means 1 of oxygen here. And then over here is 2 waters. So this is what's going to create called molar ratios. A balanced reaction acts as your bridge to convert from one thing to the other, because you get a molar ratio from a balanced equation. And what do I mean by a molar ratio? Okay. So there's a 2 in front of the hydrogen right here. Does everyone see that? There's a 2 right here. Okay. That 2 in front of the hydrogen represents 2 moles of hydrogen. Okay. So you know that big number we already talked about means you have 2 of those giant numbers. Okay. You need 2 moles of hydrogen with 1 mole of oxygen to make 2 moles of water. So does that make sense what I'm saying? That number we put in there was actually representative of a mole. So we have 2 moles of hydrogen here, 1 mole of oxygen here, and 2 moles of water, okay? And a mole is that 6.02 times 10 to the 23rd, and also 1 mole weighs 18.02 grams of water. So basically, if we do a 2-to-1 reaction here of hydrogen to 2 moles of hydrogen to 1 mole of oxygen, we're going to get 2 moles of water. 1 mole of water weighs 18.02. So what would 2 of them weigh? 36.04 grams. So basically, one reaction of water gives you not even 10% of a pound to form that much water, all right? Which isn't very much, because if you remember right, 1 gallon of water weighs 8.34 pounds. So does that kind of tell you how big of a reaction you need to make like a cubic foot of water or 1 gallon of water? It's a pretty big reaction. Requires lots of stuff to do that. So with a balanced chemical equation, I was telling you it means each one of those things becomes a molar ratio, okay? Those molar ratios are your bridge between the different atoms or different molecules, depending upon what you're dealing with. Because these ones would be considered atoms. This is considered a molecule because it's a compound, all right? These are conversion factors, okay? So they're not written this way, but it basically 2 moles of hydrogen equals 1 mole of oxygen with a balanced chemical equation. And you can write them as you see here as a fraction, and you can flip it if you have to. These can be flipped. 2 moles of hydrogen equals 2 moles. Well, see, there's 2 here, and then there's a 2 there. So 2 moles of hydrogen equals 2 moles of water. So this is your bridge between, like, if I'm telling you how much of this you have, and you want to figure out how much water you'll get, this is the bridge you'll use. And then here, on the other side, we have 1 mole of oxygen equals 2 moles of that. So this is your bridge between these two. This is why stoichiometry is different than unit conversions. The conversion factors you get come from 2 places for the most part. They come from a balanced equation, and they come from molecular mass that you found using the periodic table. So that is what's mostly confusing about this to people. The canceling, the flipping and all that stuff, you know, people go, oh yeah, I get that. But then the minute that we get to having to find conversion factors out of these equations that are balanced and out of molecular masses, things change real quick, okay? So how do we use a molar mass or a molar ratio? Okay. So let's start with like this example here. I'm going to go write all this out. So if you start with 5 moles, how many moles of water will you make? Okay, well, whatever. All right, so let's go balance our chemical balance an equation and look what this looks like on paper. Okay, like how would I do this start to finish essentially? All right, yes, it's written there, but I feel things written out like on a PowerPoint are kind of useless, but there isn't really much better of a way to present this to you initially other than show you and then do it. Okay, so first off, I'm going to just do the equation of water. Okay, everyone sees that. We got the water. This is unbalanced, so I got to put a 2 here and a 2 there to balance it, okay? So if we give you a reaction and it's unbalanced, you have to balance it first. That's the first thing you would do before you can start answering these questions, okay? So there, I balanced the reaction. Now, the question was, if I have 5 moles of this, how many moles of that am I going to get? All right, so you write what you start with, just like any other time. 5 moles of H2. That's over 1, okay? Well, I want to know how many moles of water I'm going to get. So this is where our molar ratio comes in. You use your balance reaction to figure out your molar ratio. So I know that 2 moles of hydrogen will give me, look, 2 moles of water. So I know that 2 moles of H2 equals 2 mole of H2O. This is the molar ratio, and it comes from this, 2 and 2. You see that? And remember, you can write this as a fraction. So 2 moles of H2, 2 mole of H2O. Does everyone agree with that? Because you got that from your chemical reaction. This is known as your molar ratio. Not ration, molar ratio. And this serves as a bridge between reactants and products. Because this comes from the chemical equation and it allows you to switch to any one of these to figure out how many you need, okay? So just like on the other ones, you multiply this way, so 10, the mole there cancels. 5 times 2 is 10, divided by 1 times this. So you're going to get 5 moles of H2O. Okay? So I just wanted to show you like a start to finish on that, how that would work. If I gave you an amount of water or hydrogen, I said this is how many grams of hydrogen you're going to use, you can figure out how many grams of water you would get too using this same thing, but we're not to that point yet, okay? So molar ratios, as you see, the molar ratio, okay. Oh, there it is. All right, well, let's go back and do this one, okay? 73.2 gram, okay. Oxygen, okay. So, oh, no, wrong thing, I'm stupid, sorry. Okay, so basically, it said we want to know how many of water. Okay, so this is what I was telling you right before this. Can everyone hear me fine? Getting the whole my internet is unstable. Am I good, Matt? Can you hear me?
Yeah, no issues on our end. You're coming through good. We do have a hand up.
Okay.
And
All right.
looks like
What
maybe
we got
Forrest
before I
has.
guess I do this because that could be complicated.
Okay. So Forrest, we've unmuted your mic. You want to ask a question?
I had a comment when Scott was showing his calculator. You can also use the caret key to show powers. And your video is very choppy right now, Scott. Your voice is fine, but your hand is jumping around.
Is it?
Yeah,
Okay,
I'm not
so
experiencing any issues on my end. So maybe
okay.
on your end, Forrest.
All right.
All right, thanks for the comment.
Yep.
All right. So All right, so what I was back to saying, so the question is, if we start with 73.2 grams of oxygen, given our equation, so that's our equation, right? If we start with 70, I might as well write it. We're going to start with 73.2 grams of oxygen. We want to know how many grams of H2O we're going to end with. So we would have to go find the molar mass of water. So it's going to be 2 atoms. And oxygen, right, is 1 atom. So this is 1.01. This is 16, 2.02. We've done this right already. We know what we're doing. So first off, you need this 18.02 grams of H2O equals 1 mole of H2O. Okay. That's finding the mass. So that's what you would have to do in this scenario first. Now, the next thing is we need to convert. So you write what you start with. We need to convert to moles of oxygen. Okay. Typically, the weight of a mole of something is going to come from the periodic table. And if you look at the periodic table for oxygen, which we did here, it weighs 16 grams. But you see the key here is 1 atom of it weighs 16 grams. How many oxygens are there here? Is there 1 or 2? There's 2, okay? So the thing with a periodic table is it gives you the molecular weight or the atomic weight of 1 atom, okay? Oxygen, man, I really wish I had a periodic table. I should have brought one. So there are 7 atoms on the periodic table that I call the lucky 7, okay? And they form, I can pull a periodic table on here. And show you. Maybe, geez, internet's slow. Oh, I hope I told you right. That's probably why. Wow, it's really this slow? Man. So, okay. So let's just pull up this periodic table. I don't care, just to show you what it looks like. Okay, so on the periodic table of elements, which is this thing, let me blow it up so you can all see it. There are 7 atoms that form diatomically, meaning when they are pure, they are 2. Oxygen is one of them, okay? I call them the lucky 7 because you see right here at nitrogen. So if you have your periodic table from last week, you can draw a thing around this. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So these 6 here, they form a 7. So I call them the lucky 7, looking for their 7th. It's those ones here. There's the 4 of them here and these 2. And then the 7th one is hydrogen, the lucky 7 that they're looking for. Okay. They are diatomic, meaning there's 2 of them. So when you see the weight of these things, I know there's no weights on this, but this one here, oxygen is 16, but that's for 1. That's for 1 atom. When it's pure in nature, like it is in our camera here, it's 2 of them, okay? So its true weight is 16 times 2, which is 32 grams of O2 equals 1 mole of O2, okay? I just want to point that out, that this one's a little bit different than what we would typically see because it's diatomic purely. So this is my molar weight for O2. So I'm going to put 32 grams of O2 over 1 mole of O2. All right. Now, I need to use my molar ratio. This is the bridge that your periodic table gives you to convert from oxygen to water. And it's 1 mole of O2 equals how many moles of H2O? How many moles of H2O does it form? So from the periodic, or from my balanced equation, 1 mole of O2, because you can see the reason why it's 1 is because it's mole up here, mole on the bottom of oxygen. It cancels, just like the grams here cancel. Well, it's to 2 moles H2O, and that right there, 1 comes from here, 2 comes from there in our balanced equation. Now, how do I get mole of water to grams of water? Well, that's your molar mass when you figure that out, which is 1 mole of H2O equals 18.02 grams of H2O. And that cancels and that cancels. See, I told you the conversion factors in this are going to be a little rough, all right, and where they come from. But practice with this makes perfect, okay? Like I said, we're going to be practicing this pretty much the rest of the time now, the way the PowerPoint is. So it's understanding where things are coming from and how we get there, okay? And the math on this is the same thing as like I was doing yesterday. I literally am going to go 73.2 times by 1 times by 2 times by 18.02, which is up top here. We get 2638.13. And then it's going to be divided by 1 times 32 times 1 times 1 is by 32. And I get an answer of 82.44 grams of H2O will be formed. So do you see? You can see how much oxygen you start with, and then you can figure out how much water on the end you're going to get. Okay? So back to the PowerPoint. Complete stepwise. Okay. Let's let me look at this, write it down, and then we'll do this together. HCl, calcium hydroxide. Okay. 98 grams of hydrochloric acid. Okay. How many grams of water would be produced? Okay. Okay. So let's walk through how we would do one of these. Okay. So first off, I know that I have hydrochloric acid, which is HCl, plus calcium OH2 hydroxide. Well, this is going to form calcium chloride plus water. This is an acid-base reaction. Okay. So I need to balance this thing. 2 CLs, 2. All right, this is pretty easy to balance. So hydroxide combines to form water. I have 2 oxygen here. I have 1 there. So I put a 2 to give me 2 oxygen here. Now I go to hydrogen. I have 4, so I have 2, and I only have 1 here, so I need to make that 2. Now I have 2 CLs and I have 2 CLs. Okay, so that equation is balanced. Okay. Now it says I'm starting with 98 0 grams of HCl. And I need to get to my magic water right here. That was a crappy star. Okay. I need to get to water on this side. So the molar ratio I'm going to use to convert the two is 2 mole of HCl equals 2 moles of H2O. So that's how I'm going to go from this to this. But first, I got to get to moles of HCl. So this is where I wish I had a periodic table. I should have left that thing up. Crap. So yeah, I can't believe there's not a periodic table in this thing. Okay, so yeah, when I go on break, I'm gonna go to a periodic table. You definitely want to have a periodic table for this thing because you're not gonna get to use your phone and Google it on a test, okay? But so what you need to do in order to get to moles, 1 mole of HCl, in order to get to this, we need to know grams of HCl. So you have to do the molar mass of that. So if you remember how to do the molar mass, you look at the chemical formula. So H, 1 atom, Cl, 1 atom. This is 1.01. I don't know what that chlorine is. Hold on. Chlorine. Atomic weight, atomic mass. I thought so. All right, 35.45. All right, so we'd multiply those out. Basically, you're going to get 1.01 plus that. So 36.46, 36.46 grams. So this is 36.46 grams equals 1 mole of that. Okay. So I can do 2/3 of what I got, or 3/4 of my equation now. So I got to get to moles of HCl in order to get to moles of water because of this molar ratio from the balanced reaction. So if grams of HCl are up here, where do grams of HCl have to be to cancel? On the bottom. So I know that 36.46 grams of HCl equal 1 mole of HCl. The grams cancel. And now I know that 2 moles of HCl equal 2 mole of H2O. As you can see, my moles of that cancel. Well, now I need to get to grams of this because the question overall asked for grams of water. So again, it's going to be just like this. I don't know how many grams equals 1 mole of this. So I got to do my H is 2 atoms. Oxygen is 1 atom. Times 16 times 1.01. You have to find the molar mass of these things because 1 mole of it weighs so much. So it's 2.02 plus 16, 18.02 grams of H2O equals 1 mole of H2O. So now look at your labels. I have mole of H2O on the top. So where does it have to go to cancel? Mole of H2O would have to go on the bottom to cancel, just like unit conversions, right? That has not changed. Oh boy, I got a lot of questions now. What'd I do? Oh, okay. Kiona, so thanks for Forrest. And yeah, I should probably just ask you guys. You look it up faster than me. The periodic table is on the math formula sheet. And by periodic table, it's a list of all the elements with their atomic symbol, with their atomic mass. Okay. So it's on the back of the second page. You know, honestly, I should probably just get that instead of a periodic table. So you won't have to bring one. It's on the math formula sheet, okay? On that one.
And again, that's just for the drinking water certification.
Yeah. I don't know how in depth they go into the like stoichiometry on wastewater. I wish they'd let me see their exams, but yeah, right. Anyone who's called, yeah, that won't ever happen. So anyway, now that I have 1 mole here, 1 mole of water equals the 18.02 grams of H2O. And if you're someone on unit conversions who doesn't write their labels, I'm going to tell you right now, if you do not write your labels in chemistry, good luck. You got to write your labels to know what you're dealing with because you will forget. All right. So now I'm going to multiply everything this way. So let me get my calculator. I'm going to do 98. Clear everything. 98 times 2 times 18.02. 3531.92. And then here It would be 2 times that is 72.92. I better just do it instead of guess. Yeah, okay, I was right. But now I divide these two. So I'm going to do 3531.92 divided by 72.92. And you will get 48.44 grams of H2O. So this is all the steps to a complete stoichiometry type question. Wow, right? So this is what I was trying to get at. Stoichiometry is a very involved process because you got to understand where your conversion factors are coming from, all right? So I wanted to demonstrate how this works. So there's a bunch of different stoichiometry concepts that we're going to be working through, okay? So that's what I'm going to recommend. We're at almost midway point or whatever, almost an hour in. I think my PowerPoint is done. All right, complete stepwise. Okay, yeah. So basically, though this is going to see overwhelming, all right, it's nothing more than a unit conversion, but understanding where your conversion factors come from, okay? So the remainder of the time, we're going to be going through the rest of the sheets on here and going through a ton. And there's no way I'm going to get through 12 pages of whatever. The answer keys are with this. So I'm going to recommend that we take a 10-minute break. I'm going to go get a periodic table. Or maybe I should print the math formula sheet, I guess. I could do either one. Math formula sheet might be easier though, because I can, I'll get the math formula sheet because that's what you're all going to see on the test anyway, not a periodic table. So I will get that in order to do what we're going to do. All right. So with that being said, let's go ahead and take our 10-minute break through our mid class like we always do. And then we'll come back and we are going to be working on practice questions the remainder of this. And just to make you all start, warming up to the idea that this isn't that bad. All right. What's this? Okay. So Matt, if you can, go ahead and start us off with our 10-minute timer.
All right, the clock is running and I have dropped the link in the chat for the math formula document if anybody wants to open that up or print that off.
I should have did that. It'd have been easier. Oh.
Okay, while we're waiting for Scott to return, I'm going to go ahead and start the second poll question. And this is just a pretty straightforward question. We are curious, would you recommend this course in a virtual format? All right, so the majority have responded, and I'll let this run another 15, 20 seconds to make sure that we connect with those that are coming back from the break. And then we will close this out. Scott, I see you're on there, and just to kind of give you a heads up, 96% like the virtual format.
Okay. Yeah, I'm here. I didn't go nowhere. All right. Just unfortunately thinking about how my weekend is ruined because I have to work on my truck.
All right, I'm gonna go ahead and close this poll. Turn it back to you, Scott.
All right, so everyone should probably be able to see my screen. I went and got the math formula sheet, okay? So this is what the math formula sheet looks like. A couple of things that we're most likely going to be using for what we're dealing with is here at the very bottom of the first page, there's common compounds in water. And then here is what I will be using as my periodic table. And as you can see here, they're all listed alphabetical order. The atomic symbols are here. So this might take me a couple seconds longer just because I know where most things are on a periodic table. So when I see the symbol, I know where to look. So that might take me a minute to look for this stuff, but this is what you can use. So I figure I might as well use what you guys all have access to. And I'm going to be using this pen. I hope everyone can see that. Yeah, you know, it actually kind of looks black through the thing, even though it's green. Okay, so now we're going to be looking. So this is where we're balancing equations yesterday, if you remember. The next page I want to go to is the second page behind that. I'm not going to have you balance any equations, okay? But what I do want as practice to have you all do is I want to go through, I want you guys to find the molar mass for 1, 2, and 3, okay? If you can. So I'm going to have you do this on your own. I already got a question. What is this? Oh, same one from earlier. I'm going to have you all do the molar masses for these just as practice, okay? I mean, you saw me walk through for a couple. But if you can, I'll give everyone like 5 minutes to do the molar masses of these things, okay? So obviously you need a periodic table or the math formula sheet or something like that to accomplish this, or you can Google each one of them, okay? Don't Google what the whole thing weighs. Google what sodium and bromine and that stuff weighs. All right, so with that being said, I'll give everyone 5 minutes to go ahead and do a couple of these three, and then we'll go over them together, and then we'll move on into the next step of doing unit or stoichiometry. All right, I think it's been about 5-ish minutes. All right, so the molar mass, I have Na, I have Br, I have one atom times this by sodium is 23.00 grams, and Br's bromine is 79.90 grams. So I'm going to add 23 plus 79.90. So I got to add these together. Oh, here's my calculator. Like, I don't know where my calculator went. So add those together, 23 plus 79.9. So this gives me 109. Oh, geez. 102.9 grams of NaBr. Remember, this equals 1 mole of NaBr2. 2 as in also, not 2. All right. The next one, I got PbSO. 4 atoms times 16. I know that one off the top of my head. 1 atom and 1 atom. Lead 2 sulfate is its technical name. Lead is 207.20 grams, 64 grams. 207.20 grams, and then sulfur's 30 something. Sulfur's 32.06. So I'm gonna add all these together. And come up to 303.26 grams of PbSO4 equals 1 mole of PbSO4. All right, the next one is calcium hydroxide. So Ca, O, and H, 2 atoms, and 1 atom. This is 6 times by 16. This is by 1.01. I have 32, 2.02. And calcium is 40.09. Add all those up. Those all add together equals 74.11 grams of CaOH2, or 1 mole. They equal 1 mole of it. All right, so now that we got those out of the way, these are what we're going to have to do for almost every stoichiometry question. You're going to have to remember how to do molar masses. And typically it's the molar masses of what you're starting with, and then the molar mass of what it's looking for in the long run of things. Okay. So with that being said, let's go to the next page here. Okay. So let's start to work through stoichiometry questions. Okay. And we're going to be doing simple without balanced equations now. Okay. We're going to be dealing with just how to figure out moles and grams and getting familiar with that. Okay. So yes, I know this is walking a little bit backwards from where we ended, but it's going to help build and strengthen our stuff. How many moles are 22 grams of argon? Okay. Well, I'm starting with 22 grams of argon, which is AR, I think. Yep. Of AR. It's over 1. Okay. Now, remember, I told you that the atomic masses that you'll see on here, so argon's right here, 39.95. That means 1 mole of argon equals that 39.95 grams of argon, okay? The moles on the periodic table, those atomic weights represent 1 mole of that atom or element, okay? So these are going to come directly just right off periodic table like this. So 39.95 grams of AR equals 1 mole of AR. So I'm going to have 22 because this cancels. I'm going to have 22 divided by 39.95. Which is going to give me 0.55 moles of argon. Well, I guess I could use argon if I want to write it out. Okay, does that make sense to everyone? What we're doing so far now? Okay. The next one here. How many grams are in 88.1 moles of magnesium? So, 88.1 mole. So I'm going to start being lazy. That's what stands for moles, just so you know, MOL. I guess I put it there. I'm going to start not writing it out all the time. All right. Well, you're going to go to your periodic table, or in our case, the math formula sheet. You're going to find magnesium, Mg, which is right here. I said magnesium, right? Yeah, okay. And it weighs 24.30 grams. And remember, that means per mole. So 1 mole of Mg equals 24.30 grams of Mg. The moles cancel just like we would. And then we go to our periodic table or our calculator. So this is just 1 times 1 multiply here. 88.1 times 24.30. 2,140.83 grams of magnesium. Does everyone see how this is working so far? These are weights off the periodic table because that's what 1 mole of these things weigh, all right? So why don't I give you all like 5 minutes to try these 3 here, 3 through 5, okay? Go ahead and try 3 through 5. And then we'll go over them, all right? I'll give everyone 5 minutes to do these. And then we'll move on to the next section that gets a little bit harder, okay? All right, so here we go. 5 minutes. How'd we do? Was it all right so far? All right, so how many moles are in 2.3? So I'm starting with 2.3 grams of phosphorus, which is P over 1. So I go to my periodic table here, or not, or whatever. Go to my math formula sheet. Phosphorus right here weighs 30.97 grams per mole. All right, so 1 mole, or wait, I need to put my grams of P are on top. Where do my grams of P have to be to cancel? Down here, and they weigh 30.97 grams of P equals 1 mole of it. Okay, so this is going to be 2.31 divided by 30.97. And this is going to come out to 0.07 mole of phosphorus, of P. All right, how many grams are in 11.9 moles of chromium? So I'm starting with 11.9 mole. Chromium is Cr. Number 1. So I now have to have 1 mole of Cr here. Now I got to go look it up. Chromium weighs 52 grams. So mole of chromium, they'll cancel. 11.9 times 52 equals 618.8 grams of Cr. Okay. Let's go ahead and do the next one. 9.8 grams of calcium. How many moles are in that? So 9.8 grams. Ca. Don't know why I wrote it out. So this is going to be grams of Ca, which we're going to find on our periodic table. Just 40.09, and that equals 1 mole of it. Grams of Ca cancel. 9.8 over 40.09 grams. Oh wait, no, that canceled. 9.8 divided by 40.09 gives me 0.24 moles of calcium. All right. Now let's try one of the ones down a little bit further. I'm going to do one, have you do the other, and then we will move on to other stoichiometry. Okay. How many grams are in 4.5 moles of sodium fluoride? So I'm starting with 4.5 mole of NaF. Now, if you look, I can't just do NaF, can I? I have to know its molecular weight. So Na equals 1 atom, F equals 1 atom. Sodium is 23, I think. And fluoride is fluorine. It's 19. Being there's only one, I'm going to just add them up. Okay, so typically you would have to multiply them, but 1 times each of those is, so it's 42. Grams of NaF equal 1 mole of NaF. So we got to come up with molecular weight first, or molar mass, where you can do it. So 1 mole of NaF is 42 grams of NaF. So you see what was different about this one, right? We had to go find the molar mass first before we were able to do it. So 4.5 times 42, 189 grams of NaF. All right, I'm gonna give everyone 2 minutes to try number 8. So I want you guys to try number 8, and then we will go from there to more stoichiometry. All right, so 2 minutes. Go ahead and everyone give that a try. All right. So I'm starting with 98.3 grams of aluminum hydroxide, AlOH3. So we're one. Wants to know how many moles there are. Well, I don't know how much this thing weighs, so I got to do Al, one atom, oxygen, hydrogen. There's 3, and there's 3. This is 1.01. This is 16, and this is aluminum weighs 26.98. So 26.98, 3248 grams, and 3.03. I add those together. $26.98, man. 48 plus 3.03 gives me 78.01 grams of AlOH3. That also equals 1 mole of that, if you remember now. When you do this, and it was 1 mole. So it wants to know how many moles. So it's going to be 78.01 grams of AlOH3 to 1 mole of it. So now we got 98.3 up top. Cancel off your units, and you got 78.01 on the bottom, and you divide them. 98.3 divided by 78.01. This is going to be 1.26 mole of AlOH3. All right, well, that's stoichiometry in the introductory part of it, okay? So now let's go ahead and move on and do some of the harder types of examples and how they work. So on the next page, yep, not this page. All right, let's start on this one. How do we do moles to moles? All right, so first off, we're given an unbalanced chemical reaction. All right, this is a combustion reaction. And if you remember, the trick for this one is to balance your hydrogens and make this even. Make oxygen even, okay? So I have 6 here, so I would need 3. Does that make that even? No, it does not. It would make oxygen an odd number. So the next step would be 12, because if I do times 2, makes it 12. Put 6 there, so that is the ticket. 6 oxygen. How many carbons do I got? So now balance your carbons, and you just do it. How many you got here? You got 2 times 2 is 4. Now look at our oxygens. We got 6 plus 8 is 14. So there we go. Balanced reaction. Okay, you need the balanced reaction because if you're going to be able to convert anything from in a chemical equation, if you're going to go from, in this case, we're going to go from C2H6, which is, I think that's ethane. That's the technical name of it. It's an organic compound. Either way, okay. If 4.5 moles of this is used, how many moles of oxygen? So in order to know how many moles of this you're going to need, you need to do your molar ratio here, okay? And the molar ratio comes from balancing the equations. So you have to balance the equations first. All right, so I'm starting with 4.5 mole of C2H6 is over 1. I'm going to use my molar ratio, which comes directly out of my chemical equation. Moles of C I got is on top, so where's it got to be to cancel? On the bottom. Well, now your molar ratio to get it to oxygen comes from your balanced equation here. So how many moles does it say I need? It says I need 2. And how many moles of oxygen? It says 7 moles of O2. So that would cancel. That would cancel. 31.5. Yep, so 31.5. Then divide that by 2 because 1 times 2 on the bottom here. 2. So it's going to be, so in order to do that reaction with that many moles of, I think it's ethane, you would need 15.75 moles of oxygen to do it. Does that make sense? Because we got our molar ratio or our conversion factor rate out of the chemical equation. All right. So it says if 0.3 moles of water were produced, how many moles of carbon dioxide were produced? So you just take what you're starting with, moles of H2O. It's over 1. Well, how many moles of H2O translate to moles of carbon? It's 6. Now carbon dioxide, how many moles of that do I have? I have 4. That's 1.2 divided by 6. It's going to give me 0.2 moles of CO2 were produced. So do you see how the chemical equation works for being able to determine how much of each things were made based on like the starting material or the ending material, okay? I'm going to give everyone a couple minutes to try C here. Everyone, I'll give 2 minutes to go ahead and try C. And then we'll go over that one. All right, so it's been our couple minutes. All right, so I'm starting with 5 moles of CO2 over 1. And it says how many moles of oxygen. So you look here, you look at your equation. This is where they're going to come from, moles. So it's 4 here and 7, oh crap, CO2 and 7 moles of O2. Sorry, I got ahead of myself. So 35 divided by 4, 8 point something. 8.75. 8.75, that cancel. Moles of O2 would be needed in order to get that. So do you see how, if you're like, oh, I need this much product. Well, if you know how much product you want, or you theoretically, you can calculate how much of the beginning materials you have to add to get that amount. Just remember, in the real world, it won't work out that way. You'll have to add more, but in theoretical, you can calculate about exactly what you need. And in every reaction, you always start with a theoretical and work from there. Because then with theoretical, you can calculate your percent of product reactant. And with that, you can determine how much more you would ever have to add to get what you want, okay? That's what industrial chemists do when they're trying to make stuff. All right. Grams to moles. All right, so is there only 2 of these? All right, yeah, there is. Okay. So I'll do one, you guys do the other. All right. Given the unbalanced chemical equation, we got to balance this thing. Okay, so 2 hydrogen, 3. Okay, so SO4, there's only 1, but there's 2 sodium, 2. Okay, yeah, this is easy to balance. Okay, so 2 sodium, right? 2 oxygen. How many free oxygen are over here? Treat sulfate as its own. Remember? Sulfate, sulfate. So treat it as its own thing. There's 1 and 1 of those. So 2 sodium, 2 sodium. Now look here, I got 2 hydrogen. I have 2, but then I have 2 more. So to get that to 4. And then I have 2 oxygen, 2 oxygen. It's balanced, okay? So remember, when they are blank like this, that is a number 1. I'll put them in here, but you don't need them. Okay. So how many grams of H2SO4 are needed to react with 0.75 grams of sodium hydroxide? So we're only starting with 0.75 moles of NaOH, okay? So it wants to know how many grams of this would we need or get or need, yeah, to react. So what you're gonna do with this is you're not gonna go find what the moles of this or the grams of this weighs per mole, because we can use the moles to get to here, but I will have to determine how much H2SO4 weighs. So I'm going to do 2 moles of NaOH to 1 mole of H2SO4 or sulfuric acid. Now you need to know how much this weighs in grams of H2SO4, okay? So now this is where we got to do our atomic molar mass, our H, S, and O. Got 2, got 1, and I got 4. I'm not going to write atom out anymore because you know what? By now we should know what we need. Oh, this is 16. This is 64. That's 2.02. And sulfur is 32.06. I think we just used it. 32.06. So 32.06. Got to add all those together. 2.02 plus. You guys could, if we were in person right now, you guys could razz me for not doing this in my head, but we're not, so you can't razz me, all right? So 98.08 grams, even though I bet Forrest would give me crap for not adding that up in my head. So H2SO4 and NaOH, okay? So now I have to multiply everything across the top. He didn't comment. I know he would. Forrest and I go way back. All right, 73.56 on top, and then 2 on the bottom here would make this, divide this by 2, 36.78 grams of H2SO4. Totally, yeah, I know. All right. All right, so I did A. So what we did here is we had to find the molecular mass or molar mass of H2SO4 as we did over here. We've done this a bunch, right? Because I only know that 1 mole of it weighs a certain amount, but I don't know how much it weighs unless I find it. So in this one, I want you all to do this one. You're going to have to find the molar mass of Na2SO4, okay? So go ahead. I'm going to give everyone, we'll say 3 minutes on this one. Then we'll go over it, and then we'll move on to the next one. All right. How'd we do? We do all right? All right. So let's go ahead and point 0.75 mole of Na2SO4 over, and then use my balanced equation. Says, oh, wait, nope. Don't listen to me. NaOH. Yeah, 0.7. Okay, so now I need to look at how many moles come out of my reaction. 2 mole NaOH. Use my molar ratio to convert it to my moles of Na2, which is only 1. Na2SO4. And then I need 1 mole of that. But I need to know how many grams Na2SO4 is. So now I'm going to come over here and figure that out. Go to the bottom of the page here. Na2S, there's 1. O, there's 4. 16, 23, 32.06. So 64, 32.06, and 46. That's 110, 142.06. Gotta make sure I don't mess this up. 70, 110. Yeah, okay. There. Hope you're happy, Forrest. All right, so did it in my head. So 142.06 grams of that. That cancels, that cancels, that cancels, and that all cancels. Okay. So now I got to times the 0.75. I can't do that in my head. Times this by the 142.06. 106.55 grams. And then put that over 2. 53.28 gram Na2SO4. All right. So this now, if we used 0.75 moles of NaOH in a reaction, assuming then there was no limit here, this is how much we would get of Na2SO4, sodium phosphate. All right, to the next one. The next one is pretty much the full gambit. This is where it becomes hard, so to speak. By hard, I mean more steps, okay? Is grams to grams. Grams to grams is like, yeah, that's it. It's the final stage. Okay, so let's walk through this. We're going to start with this one, which is glucose. We're going to start with an already balanced reaction, okay? Just giving you a heads up. You're not going to get that lucky ever, okay? But, okay, I lie on that. We give you a balanced reaction and softening on the F1 and 2 stuff, or when we're doing sludge calculation for precipitate, we give you a balanced reaction, but you still got to know how to do stoichiometry. Okay, so grams to grams. Glucose, this is what's produced in photosynthesis. If a plant needs 12.6 grams of glucose, how many grams of water are required? Okay, so this one I'm starting with 12.6 grams of C6H12O6. Okay, so let me lay this out for you of how this would look, okay? So I got grams of C6H12O6, correct? That's my label there. This gets me to moles of it. Now, you're going to use your molar ratio to convert from this to water. So look at your equation here and see how many moles it is. So it's 1 mole of that. And that gives me 6 moles of water. This is my molar ratio. Now, if moles are on top of water, that means water has to be down here to cancel. And then I need to know my molecular mass, my molar mass. So you can lay out the equation. You can kind of see, but what am I missing here? Missing my grams. Because you got to get grams to moles, use your molar ratio from here to switch it to the chemical you're looking for, and then use a molar mass ratio again for the one that you want grams of. Does that make sense? Yes, they're not in here. I have to figure them out. But you can see if I leave it blank that I can go from moles of it, molar ratio to convert to water. And now I need to know how much water weighs. Well, water we've done a million times already. I'll do it up here because there's some free space up here. But H and O, 2, 1, 16, 1.01, 16, 2.02. So this weighs 18.02 grams. That's the molar mass of it. Now I need the molar mass of glucose. So C, H, and O. 6, 12, 6. 16, 12.01, 1.01. So this is going to be 12.12. This is going to be 72.06, and this will be 3264.96. So 72.06. This calculator, its buttons are in weird spots compared to my other ones. I'm not used to it. So this one weighs 180.18 grams. So I put that here. And now you see I have my grams to grams because I start with how many grams and I finish with how many grams of water. Now to cancel, you cancel, 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 cancel. Because if it's on top, it's got to be on the bottom to cancel. If it's on top, it's got to be on the bottom to cancel. On top, it has to be on the bottom to cancel. So when doing a gram to gram calculation, grams to gram, you will need 2 molar masses. Okay. Anytime you do it, you will have to find 2 molar masses. If you're starting with so many grams and going to grams of something else or trying to find out what you need, you will have to do this. So when I was in chemistry in high school, yes, in high school, my high school chemistry teacher, I had, I suppose, special privileges over some of my cohorts. The chemistry teacher would let me design my own chemical reactions as long as they weren't like blowing things up. He'd let me do a chemical reaction, and then he would ask me to work out all this stuff just like this. I would have to work out how many grams of this I need, how many grams of that I need, blah, 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 blah. And the catalyst for the starting, like how you start the reaction. Some reactions just start when you mix them together. Others require, a spark or electric or something to start them, right? And he would let me, I'd have to do this and then show it to him like that I did my math right. And he would check it. All right. So your water plant's kind of the same way. If you work in treatment, you don't just add amount of chemicals, say, good enough. That was all tested over and over and over and over again to meet certain water quality parameters by whoever built your plant, whoever does your treatment schematic. Anytime you go to change that, you need to notify the state. You don't just change it. You got to have a permit, and you also will be most likely be required to do a study to show what you're going to do and how you're going to change it. Okay. So let's go ahead and do the math on this now. So it's everything across the top. So it's 12.6 times by 6 times by 18.02. Gives me 1,362.31. Now, this is all ones on the bottom, just so you know, it doesn't always end that way. And then I just got to divide by that. So 1362.1 divided by 180.16 gives me 7.56 grams of water. So that's how you do these ones, okay? If a plant needs to consume 36 grams of water, how many grams of CO2 were also consumed? CO2 and water are the chemicals that start photosynthesis, okay? The plants use light energy in their chloroplasts within their leaves to do that reaction, just so you know, might as well teach you extra stuff, right? So I'm starting with 36 grams of H2O. I need to get it to moles of water so that I can use my molar ratio to get to carbon dioxide. So I know that 18.02 grams of water, we just did it up there, equals 1 mole of H2O. Now you're going to use your molar ratio. So 6 moles, that comes right out of here. 6 mole H2O. How many moles of carbon dioxide then? 6. Now I know that 1 mole of CO2. So we knew the molar mass of water. That's why I didn't go solve for it. Typically you'd have to though, all right? Now, grams of CO2. I could tell you what it is off the top of my head, but we're gonna do it. CO1, 12.01, 2 at 16, so 32, 12.01, add them together, 44.01, so 44.01 grams. Now you go through here and do the canceling. Grams, mole, 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 mole. See how it all cancels? All right. So I have 36 times by 6 times by 44.01, everything across the top. I got 9,506.16. Now I got to divide that by these two numbers times together, because 1 times this times this. And you can see, this is how I type in my calculator. Everything across the top. No, then I'll do it here. 1 times 18.02 times 6 times 1. Which ain't gonna make a difference, but. So 108.2. So now I'm going to do 9506.16 divided by the 108.12. So I would need 87.92 grams of CO2. All right. Okay. Crap sticks. You think you are ready? I don't know. I'll do number 4 because you got to balance the reaction, all that crap. And then I will let you guys try number 5A and B. All right. In the decomposition, 1 gram of aluminum sulfide, how many grams of each element should be produced to balance the equation? Oh, well, that stinks. I changed my mind. I don't want to do it. Just kidding. 2 and 3, and this is 1. That one's really easy to balance. Okay. Decomposition means it breaks down. All right. So 1 gram of Al2S3. 1. Well, this is where I now need the molar mass of that thing. So Al, there's 2, and then S, there's 3, 32.06, and this was aluminum. It's 20, 26.98. All right. I'm gonna add all those things up. 26.98 times 2. 53.96 plus 96.18. So 150.14 grams of Al2S3 equals 1 mole. 9 use my mole ratio, so 1 mole Al2S3 to 2 moles of aluminum. This one's easy because this one comes right off periodic table. I don't have to add it. There's nothing else attached to it. So this one's 26.98 grams of aluminum. Cancel, 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 cancel. All right, so 2 times 53.96 divided by 150.14. 150.14. So I'm going to get 0.36 grams of aluminum. I do not have enough room to do the next one. So I have to write all this out, same part, but then switch this to 3S. So it's, man, I don't have enough room. All right, the 150.14 gram equals 1 mole times 1 mole of it. There's 3 moles of sulfur. So I got equals 96.18 over the 150.14. Gives me 0.64 grams of S. All right, 5A and B. I'm going to give you all like 7-ish minutes to do these two. We will go over them and then that will be the end of today. Okay. So you have to balance the reaction first. So go ahead, balance, and then try A and B, and then we'll go over them and we'll call it a day. All right. All right, let's get this show on the road. All right, so I got to balance this thing. Oh, nitrate and chromate stay together. That's good news. Okay, so 2 potassium, 1 mg, 1 chromate, 1. Okay, ta-da, balanced. 2 nitrates, 2 potassium, 2, and then you got 1 chromate, 1 magnesium, 1 magnesium, just like that, balanced. Okay, at least that part was easy. How many grams of potassium chromate are required to make 65 grams of magnesium chromate? All right, so I'm going to start with, so what I'm going to do is I'm going to sort of cheat. And what I mean by that is, you know how I laid out the 1 and then put in the numbers later? I'm going to do that first. So Mg CrO4 1 times, this would be 1 mole of it, MgCrO4. This would be grams of it, MgCrO4. And then I use my molar ratio, which in this case is 1 mole. There's no ones there, but they are there, MgCrO4. And 1 mole of K2CrO4. Then it's going to be 1 mole of it, K2CrO4, and then I need to know how much it weighs. Yeah, I'm going to just tell you, if you do the rest of this homework, you're probably going to need scrap paper. I managed to fit it in the answer key, but it's really tiny, okay? So I'm going to do the weight on one side, the other weight on the other side kind of thing. So MgCrO, 4, 1, and 1, okay? Excuse me, that's 64. Chromium is 52. I'm not going to multiply them. I'm going to just write it, because if there's only 1, it ain't going to make any difference. 24.3. So I need to add those together. So 24 point, come on, 24.3 plus 52 plus 64. This is 140.3 grams. So this one is 140.3. Okay. The next one, potassium. I'm going to do it over here. K2, there's 2, and then CrO4. Potassium weighs 39.1. This is 52, and this one weighed 64, because it's the same as over here. So 39.1 times 2, 78.2, plus 52 plus 64. This one's 194.2 grams here. Okay, so now I'm going to just do my multiplying. 65 times that gives me 12,623 over 140.3. 89.97 grams of K2CrO4. So that's the first one. Now the second one, how many grams of potassium nitrate should be produced with 65 grams of magnesium chromate? So we're using this, we're starting with the same exact stuff. So this whole half of this is the same, because I'm starting with magnesium chromate again, 65 grams of MgCrO4 over 1. Well, this time I already know what this is because I already did it. 1 mole of it. Now, balanced is 1 mole of MgCrO4. And then potassium nitrate is right here. Okay, let's pretend that that's that I'm reading it. It shouldn't say that. Whatever. KNO3 times 1 mole of KNO3 over grams of KNO3. So now I need to figure out this. KNO3 times 16. 1 there is, this is 39.1 because there's only one of them. Nitrogen, there's only one of them, and that's 14.01. And this is 48. So I gotta add those up. So 39.1 plus 14.01 plus 48 is 101.11. So this is 101.11 grams there. So that cancels, this cancels, that cancels, my molar ratio. So 65 times 2 times 101.11 gives me 13,144.3. And then divide that by 140.3. Oh, poop. Hold on. This is going to equal 93.69 grams of potassium nitrate were also formed. This needs to be changed. Yeah, whatever. But so what we just did is what the remainder of this packet is. It's all the same thing after this, okay? There is an answer key to all the pages of this, but the rest of it is grams to grams, okay? So this is as hard as it gets. What makes these complicated is understanding where your unit conversions come from. Okay, what did I do wrong? Why didn't that 2 change in the NO3 to NO6? Oh, because it remained as a polyatomic ion, Kiona. Okay, so these take practice to master. Do I have a feeling that some of you are maybe a little bit more familiar with this now or a little bit more comfortable? Yes, I do. I'm sure that some of you did learn something from this, but this will not stay fresh in your mind unless you use it. I promise you. I did not use this for 5 or 6 years. And to be honest with you, I mean, it was kind of like riding a bike. Once you do it, it comes back to you pretty easily, but it took me a while to get back in the swing of doing this. Because when I first started at State, I taught chemistry, or I taught math and treatment stuff, learning about filters and that kind of stuff. I didn't really teach anything that had to do with straight up chemistry like this does. Then I got the idea of, hey, these people should know some basic chemistry. And I'm working on a part 3, just so you're all aware. I am working on that when I have free time here and there. And I got part of it done already. So this takes practice. Do I expect you to be perfect at it? Absolutely not. Will you see stoichiometry on a 3 or 4 level exam? No, you will not. But on an F1 and 2, I guarantee you, and I promise you, they are there in the softening and sludge calculations. All right. So with knowing that, I thank you all for joining me over the last 2 weeks. Maybe I will see some of you next week in our cross connections class that is virtual, because I do also teach that. So I will be maybe doing that. And I think with that being said, I appreciate everyone being here and continue to do the work that you do, and we'll go from there. Thank you and have a great day, guys.